Okay, all right. So let us start today's session. This is session number 14. So what we have been seen, so we have been going through the characteristics of transmission line. Then we have seen the modeling of transmission line. And in the last class, we have seen about the lossless transmission line. And then we have seen the surge impedance and the surge impedance loading. And we have also solved problems based on the surge impedance loading and lossless transmission line. So basically, a characteristic impedance is defined as the square root of ratio of series impedance to the shunt admittance. And if we define the characteristic impedance for a lossless transmission line, it is called as surge impedance. So now just we have a quick recap of the surge impedance and surge impedance loading. So the first question is that the surge impedance of a 200 kilometer long overhead line is 300 ohm. What will the surge impedance of a 300 kilometer length of overhead transmission line having same parameters? So does the surge impedance depend on the length of line? The answer is no. It doesn't depend on the length of line. If we define this surge impedance, then it is the ratio of L divided by C, a square root of ratio of inductance to the capacitance of transmission line. So there is no terms comes for this length of transmission line. So the correct answer for this problem is A. Now the second problem based on surge impedance is that the surge impedance of 400 ohm means, and the options if we see that first option is that line can be theoretically loaded up to 400 ohm, and second option is that line can be practically loaded up to 400 ohm, and third option is open circuit impedance of 400 ohm, and D option is short circuit impedance of 400 ohm. So we have seen that about surge impedance. So it defines the how much amount you can load a transmission line, that is theoretically. So the A is the correct option. Now third question is that if the line is loaded with a surge impedance, then the receiving end voltage is, it is equal to the, it is first option is that less than the sending end voltage, B option is that equal to the sending end voltage, C option is more than the sending end voltage, and D is none of these. So if we are having this same, if the line loaded with surge impedance, then this receiving end voltage will be equal to the sending end voltage. And suppose if the line is loaded less than the surge impedance loading, then the receiving voltage will be more than the sending voltage. And just vice versa, if if line is loaded with more than surge impedance, then receiving voltage will be less than the sending voltage. So these are the basic questions based on the surge impedance. Now we are moving to the we are moving to the power flow through transmission line. We will first see
Uh,
the, yes,
Question number three, remaining conditions also can you write here, sir? Surge
here,
impedance. Hello?
yeah, yeah, and so you can write load impedance is,
Surge impedance.
yeah, so if load impedance is greater than surge impedance, then magnitude of receiving end voltage will be less than the sending end voltage. And if,
Next vice versa.
yes, if load impedance is less than surge impedance, then receiving end voltage will be greater than the sending end voltage. Correct?
Thank you, sir. Thank you,
Done.
sir.
So now let us see the derivation for this power flow through transmission line. We have seen problems based on that in the earlier session also, but here I have shown the detailed derivation of this power flow through transmission line. Suppose we are having this with two bus and they are connected through a transmission line having whose characteristics is defined using ABCD parameters. So this is bus 1 and then this side we are having sending end current and then this voltage is Vs angle delta. Vs we are not taking mod and thus just take it as magnitude Vs simply and then this receiving voltage is Vr at the angle of 0 degree and sending end apparent power is active power plus J QS reactive power and then receiving end power will be PR plus JQR and this you can write IR Vs is equal to Vs angle delta and here VR is equal to VR at angle. We are taking the receiving end voltage as reference. So we are taking this A value as having a magnitude at the angle of alpha and this B is taken as magnitude at the angle of beta. So we know that this ABCD parameters like IR is equal to Vs minus A VR divided by B. So put this value Vs and VR A and B. You will get this as this expression IR is equal to Vs divided by beta at the angle of delta minus beta. Delta is the power angle and this mod A VR divided by B at the angle of alpha minus beta. So we know that the receiving in complex power will be defined as 3 into VR IR conjugate. So it will be PR 3 phase. This is total 3 phase power and JQR 3 phase. So you will get, if you do this like, then putting IR conjugate and multiplying with VR, then this angle will get in just take a minus here, so it will be beta minus delta and this becomes beta minus alpha. Now if you write in the terms of line to line voltage, so this 3 will get eliminated and this VSLL VRLL divided by mod V at the angle of beta minus delta and mod A VRLL square beta divided by B at the angle of beta minus alpha. So here Vs LL is equal to root 3 into Vs and VR LL is equal to, these are all magnitude, so root 3 VR. So now just we have to separate the real and imaginary part. So if you write this in terms of Cartesian form and separate the real and imaginary part, you will get total three phase active power at the receiving end. So you will get, if you separate the real part, then you will get the terms in the then you will get the terms in cos, and this first term includes the cos term, and just imaginary part include the sine term. And similarly you can obtain the three phase active and reactive sending in power y following this by writing the equation for 3 vs is conjugate in the apparent power. So I have shown here for the uh, receiving in power. Similar way you will get the sending in active and reactive power. So these are for receiving in powers, and these terms are for sending in powers. And if you want to calculate the real and reactive power losses, then just subtract the sending in power with the receiving in power. That will be the loss in the transmission line, active and reactive power loss. Now suppose if you need to find the general expression for maximum value of sending and reactive power, then just I am writing the final expression. But you may derive this using the power delta curve. May refer the you may refer this Stevenson book. For the sending end, I am writing the for maximum sending end power, what will be the power angle, like for maximum sending end power, this delta will power angle will come as 180 degree minus beta. So PS total three phase maximum power will come as, you put this delta is equal to 180 degree minus beta in the expression, you will get mod A Vs LL square divided by mod V cos beta minus alpha Vs LL into VR line to line voltage divided by magnitude of B. So here we are putting this delta is equal to 180 degree minus B, then cos term will become, and this inside cos term will become 0, so this will be equal to 1, and this will remain as it is. First part will remain as it is, and this subtracted part will become without this cos part. And for QS three phase max, this will be mod A Vs LL square divided by mod V sine beta minus alpha. And for maximum receiving end power, generally examiner prefer this maximum receiving end power more as compared to the maximum sending end power. So you just remember this in this term, power angle will be equal to beta. In this case, maximum receiving end power. So in this case, maximum Vs LL VR LL divided by mod V sine will not come here. So minus mod A VR LL square divided by mod V cos beta minus alpha, and this QR three phase max will be minus A VR LL square divided mod V sine beta minus alpha. So these are the general expression for sending in and receiving in active and reactive powers. Still here, is there any doubt?
No, sir. No.
So now we will see the power flow through a short transmission line. So we have seen the general expression for power flow through transmission line. Now if we consider the short transmission line, in that case this A value is 1 at the angle of 0 degree. Earlier we are having A is equal to mod A at the angle alpha. So what we will do in the earlier expression, we will substitute mod A is equal to 1 and alpha is equal to 0. So we will get the power flow through short transmission line. And in short transmission line, B is just the impedance of line. So B is written as mod Z at the angle of theta. So in the place of mod beta B, we will write the impedance, and this at the place of beta we will write the impedance angle, that is theta. So by substituting these four terms in the previous expression for sending in active and reactive power and receiving active and reactive power, we will get this expression. So this is the expression for short transmission line. Now similarly we will write the expression for maximum value of sending in and receiving in case of short transmission line. Just in the previous case we have written for maximum sending in power power angle will be 180 degree minus, we are writing 180 degree minus beta, but here this impedance angle will come. So you put 180 degree minus theta, you will get PS, total three phase maximum power, that is Vs LL square mod Z cos theta plus Vs LL VRLL divided by mod Z. So again this cos theta you can write. So cos theta is nothing but it is R divided by mod Z. So you will get PS three phase maximum value as Vs LL square divided by Z square into R plus Vs LL into VRLL divided by mod Z. So we'll get the maximum sending in power in the case of short transmission line, and similarly you will get the QS max, QS3, QS 3 phase maximum value will be VSLL square mod Z sin theta. So sin theta, how you can write? Sin theta is x divided by mod Z. So this will be VSLL square into divided mod Z square into x. And similarly for maximum receiving end power, what will be the value? Theta delta is equal to theta. So just you keep in mind this expression for sending in power. For finding the maximum sending in power, you have to put delta is equal to 180 degree minus theta, and for receiving it, we have to put power angle is equal to impedance angle. And for the general case, we are writing the angle of B, so that is delta is equal to 180 degree minus beta, and for the receiving in power we are putting delta is equal to beta. So I am writing down this. So PR three phase max will be VS LL into VRLL divided by mod Z minus VRLL square divided by mod Z square into R, and this QR three phase maximum value is minus VRLL square divided by mod Z square into X. You put this cos theta is equal to R by Z and sin theta is equal to XY mod Z, you will get this expression. Now we have seen the power flow in the general case for transmission line, and then we have seen the short transmission line. Now we are moving to the lossless short transmission line, and generally this is very important because this expression you can easily remember, and examiner also directly from this expression only. So now we have assumed this short transmission line is lossless with impedance Jx. So we are define this short transmission line as R plus JX series impedance of short transmission line. And now we have considered the lossless short transmission line. So this R value will be 0. So simply at the place of J you have to put X value, and at the place of theta you have to put the 90 degree. So in the previous expression you have to put at the place of Z by mod X, and at the place of theta you have to put the 90 degree. So you will get the active and reactive power for the sending and receiving in. And A value will be similar like for the previous case. So on substituting these values, you will get the sending end active power is equal to receiving end active power, that is VSLL into VRLL divided by mod X sine delta. Like here you have to put the theta value as 90 degree, so cos 90 minus delta sine theta, and theta is equal to 90 degree, that is cos theta is equal to 0. So here this PR 3 phase you will get, and PS 3 phase you will get the similar way. So this is very important. Now for reactive power at the sending and receiving end, the expression will be different. For sending in power you will get this VSLL square divided by mod X minus VSLL into VRLL divided by mod X into cos delta. Now suppose this delta is very small, then cos delta will be approximately equal to 1. For a small delta, for delta is tending to 0, like this cos delta will become 1. So you will get this expression VSLL square minus VSLL VRLL divided by mod X for a small delta, and this QR3 phase just put second term will come first here, and this second term analogous to this QS3 phase and QR3 phase, you can find this analogous between both this expression. And if you for writing for a small delta, then you will get this term. Here you can also see that this, if you take the common between two terms, then it will be you take VRLL LL divided mod X as common, then VSLL minus VRLL, that you can write delta V. And here also this QS 3 phase, you take VSLL common, then VSLL divided mod X common, then you inside term will be VSLL minus VRLL. So delta V is nothing but VSLL minus VRLL. So in this also just remember one expression, that is enough, and you, by finding the analogous between other terms, you can remember the receiving and reactive power. Now let us see the same case. Find the expression for PS active and reactive power sending in and receiving in the case of lossless short transmission line. So, so in the previous case, for maximum power transfer, for maximum power for maximum power, we have seen that for sending in it is coming at 180 degree minus theta, and for receiving in delta is coming as theta. So but for lossless transmission line, we know that theta is equal to 90 degree. For lossless or transmission line, theta is equal to 90 degree. So in both, for both the case, you will get you will get delta is equal to 90 degree. So just put this delta is equal to 90 degree in the expression we got here, and you will get the maximum sending in and receiving in active and reactive powers. So PS 3 phase max is equal to PR 3 phase max. So sine 90 degree is equal to 1. So maximum value is VSLL VRLL divided by mod X, and for reactive power QS 3 phase maximum is equal to VS LL square divided by mod X, and QR 3 phase maximum is minus VRLL square divided by mod X. So till here, any doubt? So now we are moving towards the some important points. So first point is that real power can be transferred even when this magnitude of receiving in is greater than the magnitude of sending in. So the real power is more sensitive towards the power angle delta. This is very, very important. This real power is more sensitive towards the power angle delta. It is not that if the receiving in magnitude is greater, then real power cannot be transferred. And the second point is that reactive power can be transferred from higher voltage magnitude to lower voltage magnitude. The second and third points are very, very important. We have seen that sending for active power, it depends on the power angle sine delta. So it depends on the difference of sending in and receiving in voltage angle. While for reactive power, it depends on the voltage magnitude difference delta V. So this reactive power can be transferred from higher voltage magnitude to lower voltage magnitude. So this is very important. Means real power, the real power amount depends on the power angle difference. In the other way, you can also say the frequency mismatch. And while the the amount of reactive power flow in the transmission line depends on the voltage magnitude difference, that is delta V. So this one is depending on the reactive power flow depends on the voltage magnitude mismatch. And this real power flow depends on the frequency mismatch. And fourth point is that real power is inversely proportional to reactance X, which can be controlled by using the series reactive compensation capacity to increase the power flow. So we have seen that real power is VR into Vs. I'm not writing line to line voltage, just take it as VR into Vs divided by X sine delta. So real power is inversely proportional to the reactance. So in order to increase the power flow through the transmission line, you have to reduce the reactance. For reducing the reactance, you can use the series reactive power compensation. So I have question here, what could be other ways? Anyone can tell, if you want to decrease the reactance of transmission line, what could be other possibility? You can do one way that you can use the series reactive compensation, series capacitive reactive compensation. Other ways you can tell, Biraya Nagula,
Yes, sir.
do you know what could be the other possibility? And Ritesh Mankar,
So, increasing the power, sir, reactive power.
no, I am here we have seen what this if you want to increase the reactive power flow in the real power flow in the transmission line, then you have to decrease the reactance of transmission line.
Sir, delta also change, sir. Delta.
Yeah, delta you can change, but this what could be the other possibility to decrease the reactance?
Okay, sir.
Miss, I am asking about how we can decrease the reactance.
Okay, okay, sir.
So you can decrease the reactance by using the bundle conductors.
Yes,
That is
yes,
the
sir.
most
Yes, sir.
most other possibility. You can decrease the reactance using the double circuit line. If you are having parallel circuit line
Parallel,
for
parallel lines, sir.
yeah, double circuit line for decreasing the reactance, that will reduce the your reactance by half. And bundle conductors we use that for decreasing the reactance. And the last point is that sign convention are positive for generator if supplying real and reactive power, and positive for load if absorbing real and reactive power. So generally we don't consider here this for generator. Mainly we have focused about the load. So whenever this key, the for load it comes, then whenever it is observing real and reactive power, then it means we have to take the positive sign. And for the generator, that means inbuilt nature is that they are supplying. So that's why we have to take the positive for generator if they are supplying real electric power. And for load, the inbuilt nature is that they should absorb. So that's why if the load is absorbing real electric power, that means it is positive. That's why when we are using this capacitance, in that case capacitance provide the reactive power, so we will take the Q as a negative. Now coming to the questions part. So the first question is that a feeder with reactance of 0.2 per unit has sending in voltage at 1.2 per unit. If the reactive power supplied at the receiving end of the feeder is zero point 0.3 per unit, the approximate voltage drop in the feeder will be. So what are the values given here? You also solve parallelly with me, and whoever is getting the answer, type your answer in chat box. So reactance value is given, reactance value of the line is given as zero point 0.2 per unit, and sending end voltage is given as 1.2 per unit, and reactive power supplied at the receiving end. So QR is given as zero point 0.3 per unit. The approximate voltage drop in the feeder. That means it is asked about delta V, Vs minus VR is equal to what? You have to answer in the per unit value. So we have seen the QR expression as VR into Vs divided by X minus VR square divided by X. So substitute all the value. So QR is zero point 0.3, VR is we have to find, and Vs is 1.2 divided by X is given as zero point 0.2 minus VR square divided by zero point 0.2. So you will get 0.006 1.2 VR minus VR square. So it will be VR square minus 1.2 VR minus plus 0.06 is equal to 0. So we will get VR as you will get magnitude of receiving voltage as 1.147 or 0.0523. So here we are getting two term. So what could be the possible answer? 1.147 or 0.0523. Nagula, you can tell this answer. Biraya, hello. I think he left. Ritesh, do you know this answer? So here we have to take this magnitude that is close to the this Vs value. You cannot take this VR value as 0.0523 because this is very far value from this voltage magnitude. All the bus voltage magnitude is like approximately in per unit. They are near to each other. So you cannot take this value that is very far from this actual voltage that is we are having this sending in voltage. So we have to take the value that is close to the voltage at the other bus. So this value we will consider. So in this problem, it is asked about the approximate voltage drop that is Vs minus VR. So it will be 1.2 minus 1.147. So it will be 0.0523 per unit is the answer. Now coming to the next problem. So actually these problems we have solved in the session number 3. So just quickly revise all these problems. So in this problem, it is asked about that two bus power system with loads given and all the values given per unit, and the reactive power supplied by generators are Qg1 and Qg2 respectively, and the per unit values of Qg1, Qg2 and reactive power loss you have to find. So first be since this active power is given, like you can find from that because load demand power is 20 per unit and this G2 is only providing 15 per unit, so the remaining power comes from the G1. So the active power for the at the bus 1 and bus 2 will be V1 to V2 divided by X sine delta. From here you will get the delta. Now reactive power at the bus 1 you can get you can get using this expression, and reactive power at the bus 2 you will get this expression, and we know that line reactive power loss is, that is the difference of reactive power at bus 1 to the reactive power bus 2, you will get the line reactive power loss. And the another question asked is that you have to find this reactive power provided by G1 and G2. So for the reactive power provided by G1 and G2, so you can get like this one. At bus 1 we are having this configuration. At bus 1 this is reactive power being provided by generator 1, and this is Q1 is getting through this transmission line, and then this Q load. So Qg1 is equal to Q load plus Q1. So you will get 5 plus 1.34, that is 6.34 per unit. And at the bus 2, you can, this Q2 is coming through transmission line, and then this is reactive power coming through generator G2, and then the load is connected at the bus 2 also. So the expression for Qg2 will be Qg2 is equal to Q load minus Q2. So you will get 11.34 per unit. So correct answer for this problem is C. Now next problem is that bus 1, this is asked in GATE 2020, and bus 1 with voltage magnitude 1.1 per unit is sending reactive power Q12 towards bus 2 with voltage magnitude 1 per unit through its lossless transmission line of reactance X, keeping the voltage at bus 2 fixed at 1 per unit. Magnitude of voltage bus 1 is changed, so that reactive power is sent from bus 1 is increased by 20%. Real power flow the line under both the condition is 0. The new value of the voltage magnitude V1 per unit at bus 1 is. So we are given with V1 magnitude and V2 magnitude. Since the active power flowing through the line under both condition is 0, so we will first find this power angle. So we'll get the power angle as 0, and it is given that Q12. First we will find this Q12, then you will get in terms of X value, and it is given here also that keeping the voltage at bus to fix voltage at magnitude bus 1 is changed, so the reactive power Q12 is increased by 20%. So you have to find this V1 dash, the increased value. So on finding this Q12 dash, that is 1.2 of Q12, so you will get V1 1 dash square by divided by X. On solving this, you will get V1 dash both two values 1.12 per unit or 0.12 per unit. Since V2 is given as 1 per unit, so you have to take the values near to 1 per unit. So it will be coming as 1.12 per unit. So the correct answer for this expression is, for this problem is 1.12 per unit. Now the last problem for the today's session. This problem has been asked in GATE 2021. In this figure shown, self-impedance of two transmission line are 1.5 J per unit each, and mutual mutual impedance is given as zero point 0.5 J per unit. Bus voltage shown in figure are in per unit. Given that power angle is greater than 0, the maximum steady state real power that can be transferred in per unit from bus 1 to bus 2 is. So first we have to find this equivalent reactance between the line. So I have just recap. You can go through these series connection inductors and parallel connection inductors. So here we are going to use this parallel connection of inductors, and we have to use this subtractive coupling because, sorry, we have to use this in the additive coupling because in the given figure we can see the dot are at the same side for both the lines. So we will use the additive coupling and we will find the equivalent reactance between the lines, and you put this value in the maximum steady state real power, you will get the answer, that is mod E into mod V. So correct option is A. That's all for today's session. Thank you for, and the next session we will study the reactive power compensation. Thank you Ritesh for attending session.
Thank you, sir. Sir, I have a question, sir.
Yes.
Sir, while we preparation for gate exam, sir, if we no, one by one, sir, if we uh,
Yeah.
means complete one by one subject fully during preparation,
No, no. Try to complete two or three subjects parallelly.
parallelly, sir.
Yeah, but because if you read, if you want to read one subject thoroughly, means it will like the syllabus is vast. Means I just want to give you suggestion. Like if you are reading power system is like if you see the syllabus, it is very vast. But if you see the problems from the from where it is asking, it is very narrow. Other subject is also like that. If you think na ki I will complete this subject first, then I will study the other subject, that will never going to happen. Because if you want to just go through briefly, like you are reading from the top view, not going deeply inside. You are reading top view like you are going you are going to the face problems where it is being asked in gate exam, not going to like read all the things we are having deep inside any concept. So it will take more time if you read two or three subjects. Like suppose today I am not in mind to read power system, so let us study power tonnage network, electrical machine. So this will also fresh your mind, otherwise your mind gets saturated. In my suggestion this will be better. Other, if you read one subject only, then you will also, it is also like that you will never going to complete one subject totally.
No, sir, my some subjects are weak,
Yeah.
so that's why I think for a one by one completed subject.
Some subjects are big, but in big subjects you give more time. Not to try to I will study for, I will 15 days I will study only power system, and again 15 days I will study only electrical machine. In the
No, no, sir. I think I'm thinking which subject is easy for me. So I completed first one by one this subject like a machine or other, and just like power electronic subject is weak for me. So I will try to delay this subject for preparation.
no, I would suggest that you start power tonics, and power tonics is very easy subject. Power tonics and easy and scoring also, because without
Yes, sir.
without power tonics you will not score more, because if you see problem power tonics, that takes very less time. I am
Yes.
speaking honestly that power system problem sometimes it takes time, but for power tonics, if you know the concept, it will solve in 1 minute. But if you see power system some problems, it will take time for like 3 minutes, 5 minutes. That is too much in GATE exam. But for power tonics, if you having hands on the previous gate problems, and you know the this rectifier and this inverter and what are the other things, that is very simple. DC-DC converter, buck boost, these three are only the basic one for power tunics.
Yes, sir.
So I would suggest that not just focus on try to focus to complete one subject. Parallelly you should command means two or three subjects. And
Okay, sir.
right now you can give the part test, and you may start the full test also.
Yes, sir.
In which you are currently.
Sir, I am final year student.
Oh, you gave the get exam last time.
Mm, yes, sir. But last time our university exams start, so I will not give time for gateway preparation.
Okay, so no, don't worry, but this time I would say is that give more this give more time on this test also. You practice more. If
Yes,
you practice more test series, then it will be very beneficial because your hand should run in the exam. Means how many times you read, how many times you read book, how many times you watch the YouTube, how many times you finished all the subjects. But if your hand is not running in the gate exam, it is not going to score. You will not going to score. Means by default your hand should run. It will come from the test series only. So you start giving the test series, subjective test series, and one day at least you should attempt one test, at least one subject. Either part test, full test, at least one test you have to give every day.
yes, sir.
And one thing also, if you think like that, I don't know anything, then also attempt the test series. And after attempting test series, you will get realize that these questions are very easy. How I have not attempted. So this will comes after attending the means after attempting the test series. Okay.
Yes, sir. Thank you, sir.
Yeah. You are from which college, Ritesh?
I am from Sir Rajiv Gandhi College.
MP.
No, sir, Maharashtra, Chandrapur.
Okay, okay. Okay, Ritesh, all the best and start practicing.
Thank you, sir.
Thank you. Bye bye.
Bye, sir.